So now actually doing derivatives in parametric forms, uh, we actually resort to using Leibniz's method of approaching chain rule. In that dy dx, in other words, derivative of y with respect to x, which would be the slope of my curve on the xy coordinate plane, is going to be the derivative of y with respect to t because we're given a derivative with respect to t. Y is given to us in terms of t, divided by the derivative of x with respect to t, which is because x is also given to us in terms of t. It's a way of kind of dealing with the fact algebraically x and y are both dependent on t, but graphically there is no t on my graph. So for first derivatives, in other words, slope of the curve, slope of the tangent, instantaneous rate of change, do the derivative of y divided by the derivative of x, with both being with respect to t. So what we'll end up with is an equation for the slope of our curve that's in terms of t. So if I'm looking at the example, x equals t squared minus 5, y equals 2 sine of t, and we're going from 0 to pi. First, in terms of the graph, when t is 0, x would be negative 5, and y would be 0. At pi over 2, well, pi over 2 is about 1.7, which would be about 2.89. Minus 5 is about negative 2.1. And at pi over 4, this y would be rad 2, which is about 1.4. So about here. At pi over 2, or I'm sorry, that's at pi over 2. At pi is about 3.14. Squaring that is a little under 10, about 9.4. Minus 5 would be about a little bit less than 5. And then y would be 0. So what I get is starting here, I would move here. In terms of the derivative, I would need dy dt, which is the derivative of 2 sine t, which would be 2 cosine of t. I would need dx dt, which is the derivative of t squared minus 5, which is 2t. Then dy dx would be dy dt over dx dt, which for this example would be 2 cosine of t divided by 2t, or if I just had to simplify it, which I'm not required to, would be the cosine of t over t. So if I wanted to know the slope of this curve at any point along there, I just need to know what the t value is. So say at pi over 2. Well, the derivative at pi over 2 would be 0, because the cosine of pi over 2 divided by pi over 2 would equal 0. So at this point here, my graph isn't perfect because I should have a horizontal tangent there. And then second derivatives. Second derivatives in parametric form are done by taking, it's not quite as simple as taking the derivative of dy dx, because we have to remember, if we find the derivative of dy dx, we're finding it with respect to t, and that would actually give me dy dx dt. And I don't want that dt there. So we do start by taking the derivative of dy dx, but then doing that, so if I were to go ahead and find dy dx with respect to time, I'm going to need the quotient also bottom times derivative of top minus the top times the derivative of the bottom, all over the bottom squared. So I'd have negative t sine of t minus cosine of t all over t squared. And notice I am using Leibniz notation here to make it a little clearer that if I just take the derivative of dy dx, because it's in terms of t, the derivative is with respect to t. So I don't want this with respect to t. So what we do is to get the second derivative, d squared y dx squared, I want to take that dy dx with respect to t and divide by dx dt. So in other words, I'm going to take negative t sine of t minus cosine of t all over t squared and divide it by the 2t that we found here back for first derivative, which would give me negative t sine of t minus cosine of t all over 2 times t cubed. And this is my second derivative of y with respect to x, because we've taken into account that if we just take the derivative of dy dx, that's with respect to t, by dividing by dx dt, it's now back with respect to x.